from Torino. Which,
okay. Hi.
Ciao.
Ciao. Okay, let me try to share my screen. Okay. All right. So hi everybody. So I'm Andrea Cavaglià from the University of Torino, which, as Vasco said, is another one of the nodes, and we will be primarily involved in work package 1 concerning integrability and bootstrapability. In this presentation, I'll present a little bit some work that we did in this direction with these collaborators, Nikolai Gromov, Julius, Michelangelo Peretti, and Nika Sokolova over the past few years. But I'll try to highlight it. So it's very exciting to be in this network because really, as Vasco already said, many people have expertise that are closely related and complementary, and it would be great. I will highlight what are the challenges of what we are trying to do and how many people in this network have expertise that could help. So, okay, the motivation for this work package in general is one of the motivation is try to understand n equals 4 super-EM mills, which, well, it's being considered as a very interesting solvable model, hydrogen atom of our century, because in a way it's the simplest theory that you can study that encapsulates a lot of different interesting phenomena and mechanism, and it's interesting if you come from different directions. So okay, of course it's maybe it's the theory closest to QCD that we can hope that it's solvable in some sense. And at least it has the same gluon dynamics as QCD, then it's interesting as a conformal field theory in 4 dimensions, and which has a continuous coupling. So it's an example of conformal gauge theories that are an interesting complicated class of CFTs. And of course, it should also be a special kind of CFT, which through the ADS CFT duality also describes gravity, and it would be great to understand well how this can happen. And on top of that, it's also a string theory, so it's interesting for many reasons. And so in this talk, I will discuss how it's very powerful to combine 2 methods that one can use to study this theory. One is the conformal bootstrap, and the other integrability, which is a special and magical property of this theory specifically. And also I will describe how thinking about defects, which is also a very big topic that many people in this network are experts on, and many of my friends here in Torino as well. And thinking about defects can be very powerful and give additional constraints to study this theory. So, okay, integrability and conformal bootstrap. So to do a quick comparison, these are really quite orthogonal approaches, but luckily, there is a region which is very non-trivial and interesting where they overlap. So integrability emerges in this theory if we study large N, where N is the rank of the gauge group of this gauge theory. But it's still...
Andreas,
yes.
Something happened with your slides? I cannot see them, maybe.
You didn't see them from the beginning? I'm sure.
I was seeing them. Then at a certain point,
I see
Okay.
them.
Yeah, I see them.
I see them too.
okay,
Okay.
it's just me, sir.
Okay, okay. Do you see them now, Francesco?
Well, no, okay, it's just me, maybe. Don't worry. Thanks.
Let me try to. Okay, if you want, I can stop share and share again. But okay, let me try to go on.
I got it. I got them. I got them.
Yeah, thanks. Yeah, so in integrability, it's still non-perturbative in the Toft coupling, which would be, I will just call the coupling constant. It's this continuous parameter that survives in the large n limit. While it's a the theory, it's a CFT at also at finite n. So the conformal bootstrap is more general. It's applicable all in all the space of parameters. And well, they come from very different principles. So integrability is really a miracle, and it's based on some very hidden and indirect magical properties of this theory that appears when you study some auxiliary 2D world that describes some processes in the large n limit. You can think of it as the surface of the planar diagrams that organize your perturbative expansions in this limit, or the wordsheet of the string that gives you a dual description. And on this wordsheet, the excitations are supposed to interact like integrable solitons like in the KDV theory, so with some special elastic interactions. And this is the origin of this integrability that constrains in a very indirect way how the full four-dimensional theory behaves. And instead, the conformal bootstrap is based on theory-independent general principles like the ones that Vasco already described. So this conformal symmetry, the OPE, locality, and unitarity. And these principles, except for the existence of the conformal symmetry, they're not used, and they're basically not easily visible in the integrability approach. In particular, you don't see the locality of the four-dimensional theory, the existence of an OPE. That's why they're really based on different assumptions, and combining them can be very powerful. So using integrability, so we make progress, we focus on one particular theory. Although, of course, if we learn to do things in n=4, probably this would be transferable, these methods, to other special theories like ABJM and other interesting holographic CFTs that also happen to be integrable in the same way. While in the conformal bootstrap, you can ask things in a different way. You really think about the space of theories with a given symmetry and try to explore this space in general. And the results you can get are also a bit different. So integrability, when you understand how it works, in principle, will give you really exact analytical results. And I will now discuss some observables. Unfortunately, we don't understand how to solve all observables even in the planar limit. While at least the bootstrap approach that I will study, and I think it's fair to expect that at finite coupling, at finite Toft coupling, usually we would expect to get some islands for allowed data rather than or at least it would be more difficult to get results with infinite theoretical precision. So here is a plot, the same one that Vasco showed from this seminal work on the conformal bootstrap that showed, so if we use these constraints given by the axioms of a CFT, you can find that there are some allowed and excluded region in the general theory space with some under assumption of some properties. And one fact is that if you ask these questions, making some fairly general assumptions, it happens that some very interesting theories can live on the boundaries of the allowed regions or very close to the boundaries. And this is the example, for example, of the 3D SYM model. So n equals 4, it seems to be hidden a bit deeper, because if you ask the questions in the same way, usually you will find that the theory at finite coupling will lie inside the generic bounds that you get. And so therefore, it's to try to improve these bounds and get close to the theory, so help the bootstrap to focus on the theory we want to solve. So what we call bootstrapability is the idea of supplementing the conformal bootstrap plus some exact data that we get from integrability. And so in general, it's an example of supplementing a bootstrap with data that also has been applied, and it can be applied in many other different directions. For example, even using phenomenological or experimental data and combining them with bootstrap for the S matrix, for example. And yeah, so in general, it's also an interesting theoretical question how to make the bootstrap converge, how to use data in the most efficient way when you have them. So to explain a bit how this goes in n equals 4 and what are the challenges, let me focus on some nice family of observables that are a nice laboratory that are, so they're interesting observables in gauge theory, which are essentially come from the study of Wilson lines. So here we want to study a special kind of supersymmetric Wilson line that there is in this theory, and the correlation functions on top of this Wilson line. So these are correlators in a way that will be very relevant later. You can think of them as they parameterize small infinitesimal bumps on this line. So in principle, by knowing all the correlation functions of operators inserted on this line, it should be equivalent to knowing the deformations of the shape of the line. But so for a moment, let's focus on these particular correlators, and they satisfy their own simplified version of the axioms of a CFT, which in this case are the axioms of a CFT in one dimension. So the first axiom is a transformation rule when you have correlation functions and you look at them at points related by a fractional linear transformation, which is a conformal transformation in 1D. And they have to transform in this way, where associated to any operator, there is a specific parameter, which Vasco already introduced, which is the scaling dimension. And then the second axiom that also Vasco already introduced is the operator product expansion. We can fuse together two operators to find a superposition of all other possible operators with some OP coefficients. And these two families of parameters, delta and the OP coefficients, form the CFT data that define the theory. So then there are bootstrap equations also here, which if we focus, let's consider a particular 4-point function of the simplest operators of this theory, which are some operators which happen to have exact dimension 1. And they are called tilt operators. They will be important in the what I will say at the end of the talk. Their 4-point function of these 4 identical operators using crossing symmetry implies one constraint, which is this equation here. So this equation involves, some unknowns that are the OPE coefficients, where you fuse 2 operators and build another one. And also, in principle, the spectrum of the operators that you can produce is unknown. And this sum should give a known explicit function. So these are functions of the cross ratio that parameterizes the position of the 4 points. And these functions G and F are completely fixed by conformal symmetry. And F also contains explicitly the coupling constant. So this theory has this continuous parameter, and through the analysis of supersymmetry, this function was essentially fixed. So we know in this function, we know on which point of this continuum of theories we are. And okay, so what integrability gives us is a full knowledge of this spectrum as functions of the coupling constant, which is a big boost of our knowledge with respect to the situation in a pure bootstrap approach, where we would also try to find what are the possible values of the spectrum. And so here I just want to mention that the method by which we know the spectrum is one of the nicest results so far of the integrability approach, and it's through some equations that are called quantum spectral curve equations. And well, through these 2 figures, I just want to say schematically that these are equations that are a sort of describe a problem of constraining some functions on a Riemann surface, some auxiliary functions called Q functions. They are constrained through the fact that they have some branch cuts and they have some monodromy conditions. And in principle, solving this problem, each solution allows us to extract the dimension of one operator through these Q functions expanded in some limit. And so the equations are exact. So in principle, through this method, you can compute the spectrum. The only limitation is that a study that one needs to do state by state. So far, we don't understand the method to, for example, extract from these equations information about how the spectrum behaves at, asymptotically at large delta, how the density of states behave. But we have essentially data with unlimited precision. Another thing that I want to mention is that although we don't understand how yet, it is expected, and there are some checks in some limits, that these Q functions are more useful than just giving us the delta, but in some sense, they are also building blocks to compute more complicated quantities like the OPE coefficients themselves. And so this is also a direction that on which there has been progress in recent years, and also ties with the objectives of this network, but it's outside the scope of what I'm discussing today. So for what I'm saying today, unfortunately, we don't yet know this magic formula to extract exactly the OPE coefficients. So we'll try to bootstrap them. And okay, so let me now describe a bit how try to very schematically say something about these very well understood methods of the numerical conformal bootstrap. And so the idea is that we have this equation that I wrote before, where we have a sum over these functions of the cross ratio, and we can view them as vectors in a vector space of functions. Or, for example, we can choose to convert this literally in an equation for vectors by taking derivatives of this equation in the cross ratio at some point. And then the equation will give us this type of identity where we have a sum of many vectors with some coefficients that are positive because they are the square of these real OP coefficients, and they should sum to another known vector. And we can, so the point here is that delta is a parameter. For each state, we have a different direction of a vector in this higher dimensional space. And this equation gives us some consistency conditions. So because the coefficients are all positive, for example, if we had this vector f were to be aligned like this, so if it were to be separated by a hyperplane from the envelope of all the other vectors, then this data would be not consistent. It would be impossible for it to be obtained as a linear combination of the other vectors with positive coefficients. Instead, in a situation like the one depicted in the second picture, the data are consistent. And these numerical bootstrap methods essentially are a way to try to exclude data by trying to find in these hyperplanes. So in this case, we know that our spectrum is consistent, so this test would be passed with the spectrum that we get from integrability. Let me also mention that in this method, one can test a few low-lying levels and treat all the rest of the spectrum as something that is generically unknown. So it's a powerful method because it allows you to study this envelope of all vectors with all possible deltas above a certain cutoff, which parameterizes where you stop keeping track of where the states are. But so then let me say how we put some bounds on one OP coefficient. And the idea is you just bring this the term corresponding to the first state of your spectrum on the right-hand side of the equation. And now you have on the right-hand side this other vector, which is parameterized by C1. And you want to see, again, if it lies within the envelope of the region defined by all the other possible vectors. And this gives you some bounds on an allowed range for C1, as illustrated in this picture. Okay, so the idea is so let me now try to say why giving input on the spectrum of integrability improves these bounds. So if we know very little of the spectrum, we would need to assume some ignorance of where the states are. And therefore, we would need to include in this family of vectors that define our envelope region all the possible values of delta above some threshold. If instead we know the spectrum, we can use the information that we know that there are some gaps. For example, this is the level delta 1, and we know that delta 2 arrives only after some gap. So we can remove from this envelope region all the states that have delta here. And then we can use that there is another gap here. So this makes this envelope region smaller, and therefore we will find some better bounds for C1 in this way. And so if you use this method, for example, you get actually for the first OP coefficient some very, very narrow bounds. So this is a plot where this first OP coefficient is plotted as a function of this coupling constant. For each value of the coupling constant, you run this algorithm. using essentially just the knowledge of the gap to the next state. And you find some upper and lower bounds that are so close that basically they allow you to build a plot of the function. In this case, it has at worst 2 or 3 digits of precision, and then it improves. And so this is another example where you can ask questions directly on the value of a 4-point function and build a plot for many values of the cross ratio. And so here, for example, so on this axis, we have this cross ratio that parameterizes the position of the points. And we have in general some large region that would be an allowed region for a generic theory. So for example, here on the boundary of the region, there is the value of the correlation function for a theory of free fermions. And as you vary the coupling constant, our theory related to n equals 4 occupies a very tiny space, allowed space in this region. So each curve here is a value of the coupling constant, and it's defined by a upper lower bound, which are very close. Okay, so this all looks good, but let me explain what are the challenges. So as I said, so the basic mechanism by which you gain information from the spectrum is that the gaps shrink the constraints for other quantities, but this spectrum is very complicated, and at some point it becomes very dense, as you can see from this picture. So essentially adding information on where are the states is not gonna have a big impact because at some point you work at a given resolution of your vector space given by how many derivatives you consider, and at some point just pumping more states in the spectrum is not gonna improve the bounds anymore. So there is this problem that in principle integrability gives us all this information, but we don't have a good way to exploit it yet, the high part of the spectrum. Also, another limitation is that if we run the same algorithm, definitely the results are much less sharp for OP coefficients that correspond to the production of higher excited states. So these are the regions obtained with the same algorithm, upper and lower bounds for 2 other OP coefficients. And you can see that the resolution is much worse. So let me describe some ways that one can then proceed and try to improve the situation. Okay, so speculatively, maybe we need new ideas. So maybe there are other ways outside the Euclidean conformal bootstrap that one can make use of this information on the high part of the spectrum that in principle it can be extracted from integrability. Well, another way that it's while this was more speculative, another way is that definitely one can consider systems of more correlation functions where we consider also the excited states to be not just this protected operator, but operator with non-fixed scaling dimension. And this is something that normally you cannot do in a pure bootstrap approach because you don't know these dimensions of the non-protected operators. And this should allow us to focus on these OP coefficients for the excited states, if you use this excited state as an external operator. And then there are ways, what I really briefly want to describe now in a couple of minutes, and then I'll close, is the role of considering defects. And these are ways to introduce really new information into the system, which comes also from integrability. So there are several ideas one can consider, but let me focus on this idea of the defects. So the idea is that there is information on the theory that comes from the fact that this line is embedded in a larger theory. As we said, these correlation functions on this Wilson line are a small parameterization of how it can move in the bigger theory. And we have some constraints because either it's the bigger theory that has some symmetries and tells us what should happen if we move the defect in a certain way, or in some cases, we have additional data from integrability. And one such case is, for example, if we form a cusp in this Wilson line. So this literally means that we can bend the defect. You can also do it in some internal space, but for the sake of clarity, you can think of really joining these two halves of this one DCFT inside that 4D space by forming an angle. And this configuration, which is a sort of interface of these two rotated 1D CFTs, in the 4D theory is divergent, but this divergence is universal. It's described by so-called cusp anomalous dimension, which is also known from integrability at all values of theta. So the idea is then that this, if we can map this back to the original theory, this will give us some additional identities. And briefly, I'll just show it in a picture, but this is what happens. You can expand in the small angle. And because this rotation of the line, this is what we know from our friends who studied defects, is that are parameterized by inserting this tilt operator. When you consider this rotation of the line and then re-expand that small angle, you get some additional identities that come from integrals of this 4-point function. So this essentially gives you some additional identities, and you can see from this picture that they allow to improve the bounds on your data. So briefly, and I'll close here, there should be many more identities like this, many constraints. You can imagine expanding at higher order in theta, but also other things. And hopefully this is a way to insert more information in the system. And it's an approach that seems very promising. So in conclusion, it looks very promising to combine all these methods, conformal bootstrap, integrability, and also including all kinds of information on defects. And so it looks very promising to interact among many people with all these different fields of expertise. And to close, let me just say who are the nice people here in Torino, especially, so there are these people who will be, so we are primarily involved with Work Package 1, and our group involves all these very nice people, in particular permanent people are Lorenzo Bianchi, Marco Billò, Marco Maineri, and Roberto Tateo. But I also want to mention that on the topics of the Work Package 2, there is also this group of Maria Elena Boglione, Emanuele Roberto Nocera, and Andrea Signori who work in very related things, so you might also meet them. And yeah, and with this, thank you very much for your attention. So.
Thanks a lot, Andrea. A nice presentation. So, are there any questions from for Andrea? That curiosities or questions?
Maybe I have a small question.
Okay.
So one of the observables with a defect could be also, let's say, two-point function of bulk operators in the presence of the defect.
Yes.
So typically there's this problem that you don't have the two positive channels to do normal bootstrap, but I was wondering if maybe with integrability you can estimate the signs of, let's say, you have the bulk OP coefficient and the one-point function. If you have a way to estimate the sign, then you would be able to do bootstrap also in that case.
You mean the sign for the expansion of one bulk operator on the defect? Is it?
So no, the bulk to defect is fine. If you take two equal operators, you get something squared, so you know the sign.
Okay.
What you don't know is the one-point function of an operator in the presence of the defect.
Okay, yeah.
Sign of that thing and the sign of the three-point function of, let's say, the fusion of two bulk operators into a bulk operator.
Right. Yes, I see. Yeah, indeed. So I have never started thinking about it, but I think, yeah, these bulk defect setups would be very interesting also to consider. And it's the way in which, yeah, this defect will talk also with the bulk operators and their CFT data. And yeah, but in terms of integrability, I think it's by itself, it's not ready yet to compute these quantities, except maybe a small coupling.
Okay, so not even the sign.
Yeah,
I see.
yeah. I think either it computes everything or yeah. No,
see.
but yeah, maybe with coupling one can see the sign.
Right.
Integrability. Yeah.
Thanks.
Thanks.
So, oh, no. It is. Hello, we are here.
Hi.
And you are in Torino with a group of Maria Elena and Oscar and so on. Have you explored some common project with this group up to now, or have you?
So now, not yet, but yeah, maybe this
An occasion.
4 years will be a great occasion. Yes.
Okay, thanks. Okay, so